2 is N2 and that of gas 3 is N3. So the pressure exerted by gas 1 would be P1. It will be equal to N1, which is number of moles of gas 1 into RT by V, where V is the total volume. Similarly, we can write P2 is equal to N2 RT by V, and P3 is equal to N3 RT by V, and the total pressure of the mixture of gas will be P is equal to P1 plus P2 plus P3. Now let's see Graham's law of diffusion. This law states that the rate of diffusion of a gas is inversely proportional to square root of the density of the gas. So if the rate of diffusion is R, then R is directly proportional to 1 by root under rho, where rho is the density of the gas. So from here we can write that R into root under rho is constant, or R1 rho 1 is equal to R2 root under rho 2, or R1 by R2 is equal to root under rho 2 by rho 1. So as we have already derived that density of a gas is equal to Pm by RT, where P is the pressure of gas, M is the molecular mass of the gas, R is the universal gas constant, and T is the temperature. So at a given pressure and temperature, that is when pressure and temperature is constant, we can say that density is directly proportional to molar mass, that is M. So we can rewrite this equation as R1 by R2 is equal to root under M2 by M1. Now we will define the degree of freedom of gas molecule. Degree of freedom for a gas molecule is defined as the number of velocity components needed to describe the motion of a molecule completely in three-dimensional space. It can also be defined as the number of possible kinetic energies associated with the molecule due to its translation along three axes, due to its rotation about three axes, and due to its vibration in various modes. So for example, take the case of a monoatomic gas molecule. So let's say this is our three-dimensional axis, this is our y-axis, x-axis, and z-axis. So a monoatomic gas molecule can have motion along any of these three axes, that is, it can have motion along x-axis, along y-axis, and along z-axis. So here we can associate three translational kinetic energy to this monoatomic gas molecule. Now the monoatomic gas molecule has a zero moment of inertia because they are point mass. So there won't be any kinetic energy which is associated with its rotation about any of the axes. So we have three kinetic energies because of translational motion. Also, the rotational kinetic energy is almost zero because the moment of inertia of a monoatomic gas molecule is zero because they are point masses. So there will be zero kinetic energy which is rotational in nature. Also there will be zero kinetic energy for the vibration because a single monoatomic molecule cannot vibrate. So in total we have three kinetic energies which can be associated with a monoatomic gas molecule. So the degree of freedom of a monoatomic gas molecule will be 3. We represent degree of freedom as small f, so f will be equal to 3 for a monoatomic gas molecule. Now similarly, the value of f is 6 for diatomic gas molecule, and there is also a formula for degree of freedom. Degree of freedom is equal to 2 by gamma minus 1, where gamma is adiabatic constant. We'll learn about adiabatic constant in further chapters. So for now, keep in mind that degree of freedom for a gas molecule can be given as 2 by gamma minus 1, where gamma is adiabatic constant for that gas molecule. Now let's discuss law of equipartition of energy. This law states that the average kinetic energy per degree of freedom for a gas molecule is half kT, where k is the Boltzmann constant. So for a gas with f degrees of freedom, on an average the total kinetic energy associated with the gas molecule is nRT by gamma minus 1, where gamma is the adiabatic constant for the gas. Now we can derive this formula as well. So according to the law of equipartition of energy, the average energy per degree of freedom is half kT. This is average energy per degree of freedom for a single molecule. So for f degree of freedom, the average kinetic energy would be f by 2 kT, and suppose we have n moles of gas, so average kinetic energy for n moles of gas having f degree of freedom this would be f by 2 into kT into n into capital N, where capital N is Avogadro constant and n is the number of moles of gas. So we know that Boltzmann constant is nothing but R by N, where N is the Avogadro constant. So now we can cancel out Avogadro constant. So we have FRT by 2, FRT into N by 2. Now we have already seen that F is nothing but 2 by gamma minus 1. So replacing F with 2 by gamma minus 1, we are left with nRT by 2. So after cancelling out 2, we get nRT by gamma minus 1. So this is the kinetic energy of n moles of gas having f degree of freedom. Now we will derive the pressure formula for ideal gases. Let's see this animation first. So here we have an ideal gas which is confined in a container. This is one of the gas molecule. The velocity of gas molecule is c, and we have broken down this velocity in three components, that is along x direction cx, along y direction cy, and along z direction, that is cz. So the kinetic energy due to the velocity along x direction would be half m cx square, and kinetic energy due to velocity along y direction would be half m cy square, and due to velocity along z direction would be half m cz square. Here m is the mass of one molecule. Now law of equipartition of energy says that the average kinetic energy per degree of freedom is equal, and it is equal to half kT. So these three kinetic energies must be equal. So from here we get cx square is equal to cy square is equal to cz square. Now the velocity of the molecule is c, where c square is equal to cx square plus cy square plus cz square. Now cx is equal to cy is equal to cz, so we can write that c square is equal to cx square plus cx square plus cx square, or 3cx square. So we have cx square is equal to c square by 3. Similarly, we'll have cy square is equal to c square by 3, and cz square is equal to c square by 3. So we need to keep this result in mind. Now suppose this molecule, it collides with the wall A, B, C, D. Now the momentum of this molecule before collision will be m into cx, and momentum after collision would be minus m into cx, because the collision is elastic in nature, so the velocity of the molecule will reverse. So the change in momentum will be two mcx. Now let the length of this container is a. So here we get 2 mcx as delta p. Now the velocity of the gas molecule along x direction is cx. So after the first collision, this molecule will travel the distance of 2a before colliding with the same wall again. So the time taken by the gas molecule to travel the distance 2a would be delta t is equal to 2a by cx. So after this time interval, the gas molecule will again collide with the wall ABCD. So the average force which is being exerted by this gas molecule due to this collision would be F equal to delta P by delta T, which is equal to 2 mcx by 2a by cx. So the average force is mcx square by a, where a is the length of this container, and let's say that b is the width of this container and c is the height of this container.